If A is similar to a diagonal matrix D, then D must have the eigenvalues of A on its diagonal. And this is by theorem 4.22e and theorem 4.15. So, writing D equals P inverse AP, and D is a diagonal matrix whose diagonal entries are the eigenvalues of A, lambda 1 through lambda n. Write P equals P1 Pn. Then AP is equal to PD. So we get that A P1 Pn, well, this is going to be equal to P1 Pn times this diagonal matrix, lambda 1 through lambda n, and then using what we know about multiplication of partition matrices, this is AP1 APn equal to lambda P1 lambda, and so it's lambda 1 P1 lambda n P1 n. Bleh. So in other words, equating these columns, we get that A P1 is equal to lambda P1 and dot 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 A Pn is equal to lambda. I keep doing that. This is lambda 1 P1 and lambda n. Let me rewrite that a little bit so it's clear. Lambda n Pn. So in other words, the columns of P are eigenvectors of A. And moreover, because P is invertible, these eigenvectors are linearly independent. This proves part of the following theorem. Let A be an n by n matrix. If P is an n by n matrix whose columns are linearly independent eigenvectors of A, then P inverse AP is a diagonal matrix with the corresponding eigenvalues of A on the diagonal. Although we didn't prove this just above here, we actually proved the next statement. To show this is just an application of block multiplication, just as we did above. On the other hand, if P is any invertible matrix such that P inverse AP is diagonal, then, by what we showed above, the columns of A are linearly independent eigenvectors of A. And from these two parts, we conclude that A is diagonalizable if and only if it has n linearly independent eigenvectors. Which brings us to the goal of the rest of this course, and that goal is to find enough linearly independent eigenvectors of a square matrix.